Starting out the assignment, we have problem 15.196. We are moving backwards, so this was the problem. A 3-inch radius disc spins at a constant rate of omega sub 2 equals 4 radians per second about an axis held by a housing attached to a horizontal rod that rotates at a constant rate omega 1 equals 5 radians per second. Knowing that theta equals 30 degrees, determine the acceleration of point P on the rim of the disc. So we started out with our equation for angular velocity. So that's our omega equals omega 1I plus omega 2k. And then we can substitute our values in there and solve that equation. And then we're going to have our second equation, alpha equals omega dot OXYZ. And then went through, simplified that equation down to omega 1 times omega 2 times j, and then we plug in our values there and we get a negative 20j. So that's our alpha value. And then moving on from there, we're going to try to find our r sub p, and that equation we're going to use our radius times the cosine of theta plus sine of theta. So we plug that in for our v sub p equation, which is omega cross with r sub p. And so we've got the equations there, and that's going to give us our answer of negative 0.5i plus 0.87j plus 0.63k feet per second. So that's our v sub p. And then we solve for our acceleration, a sub p. So we've got the equation there, ran the cross product, and that gives us negative 3.46i minus 5.13j plus 8.66k feet per second squared. Alright, next problem we have problem 15.176. So knowing that at the instant shown the rod attached at A has an angular velocity of 5 radians per second counterclockwise and an angular acceleration of 2 radians per second squared clockwise, determine the angular velocity and the angular acceleration to the rod attached at B. So we start out at the point B. The sum of the angles is 180. So we know the sum of angle 70 degrees and angle ABP is 180. So we can find that our angle ABP is 110 degrees. And then considering the triangle APB, the sum of the angles is 180. So we used that summation to find that APB is equal to 45 degrees. And then we can use our law of sines to solve for AP and BP. So we get AP equals 0.26 meters and BP equals 0.12 meters. And then we've got to think about the unit vectors along the x and y directions as the angular direction in K. So we know that link AP is at an angle of 25 degrees, and so the coordinates of the point P with A as a reference are 0.11i plus 0.24j, and the link BP is an angle of 70 degrees. So we find the point B as a reference, and we find that position vector R P over B is 0.11i plus 0.04j. And then we go along to use our equation V sub P over F equals U cosine 20i plus U sine 20j, because our relative velocity is at an angle of 20 degrees. And then we can use our equation V sub P equals V sub P prime plus V sub P over F. Plug in our values there and solve for it, and that's going to give us an I and J equation, which we take the x and y components and solve for U and omega sub BP and get those values there. Move on to the rest of the problem. Okay. So now we can go ahead and substitute those values back into the equation for v sub pf, and then next that's going to give our velocity there. And then next we're going to be finding our acceleration, so we're going to use our a sub p equals a sub p prime plus a sub p over f plus ac, and then we manipulate that to get our equation here where we get a sub p equals a sub a p cross r sub p a minus omega squared sub a p times r sub p over a. Plug in our known values and solve for that. We're going to get a negative 2.3259 minus 6.246 J meters per second squared. And then go back again and use our equation a sub p equals a sub bp plus r sub pb minus omega sub bp squared times r sub pb, and plug in our values once again. Alright, and then next we are wanting to resolve the relative velocity along the x and y directions. So we know that a sub pf equals u dot, which is another sine cosine situation with 20 degrees. So knowing that, we're going to substitute that in for our a sub c equals 2 omega sub bp cross with v sub p f. Substitute those new values in and do some solving, and that's going to give us our a sub c, and then we're going to get our a sub p. And then we can compare the terms for the equation in the x direction and the y direction and solve for our u dot and our alpha sub bp, and we're going to get our u dot equals 3.06 meters per second and our alpha sub bp equals 81.1 radians per second squared in the clockwise direction. Okay, let's get that to focus. Alright, so we've got problem 15.114. 3-inch radius drum is rigidly attached to a 5-inch radius drum as shown. One of the drums rolls without sliding onto the surface shown, and a cord is wound around the other drum. Knowing that at the instant shown at the end of D of the cord is the velocity of 8 inches per second and the acceleration is 30 inches per second squared, both directed to the left, to determine the accelerations of points A, B, and C of the drums. So we start out with our equation, v sub d equals v sub b equals 8 inches per second, and then we go for v sub b equals ab omega, and we can solve that for omega and get omega equals 4 radians per second. And then we have our a sub a is up, a sub b is left, is 30 inches per second squared left, plus a sub b sub n up, a sub g is to the right, and then we can also solve for our alpha and get that alpha equals 15 radians per second squared. And then we take those values and plug them into our equation for a sub a, and we've got a sub a equals a sub g plus a sub ag sub t plus a sub ac, ag sub n. And then we solve that, we can go through and solve that for our alpha and solve that for a sub a and get that equals 48 inches per second squared up. And then we repeat the same exact process for a sub b and a sub c with their respective values, plug those in, and we get our a sub b is 85.4 inches per second squared, up and to the left at 69.4 degrees, and a sub c equals 82.8 inches per second squared, down to the left at 65 degrees. Okay, so problem 15.109. Knowing that the instant shown at the crank BC has a constant angular velocity of 45 rotations per minute clockwise, determine the acceleration A of point A and of point D. Okay, so we start out doing some geometry and we find our angle BAC, using the sine of that, which is 4 inches over 8 inches, and we get that angle equals 30 degrees. And then we know our angular velocity of BC is 45 rotations per minute clockwise, which we convert to radians per second, and we know that V sub A is upwards. V sub B we can calculate using our BC times omega sub BC, and we find that our V sub B equals 18.8496 inches per second, and that is vertical, up rather. And then we move on. I'm sorry, I'm yawning. We move on to we've got our V sub A equals V sub B, which we solved earlier, which is that 18 number. And then at BC, we get A sub B sub T equals BC sub alpha equals 0, and our A sub B sub N, which equals BC times omega sub BC squared, which we can solve and get our A sub B equals 88.827 inches per second squared to the right. And then at rod ABD, we have our alpha sub AD is counterclockwise, and our acceleration of A is upwards. And then we have our acceleration of A formula, which is A sub A equals A sub B plus A sub AB sub T plus A sub A over B sub A. And then we can substitute our known values in for that equation and solve that to get our A sub A, which is 51.3 inches per second squared downward. And then repeat the process with our equation for A sub D and get that A sub D is 184.9 inches per second squared at 16 degrees up and to the right. Problem 15.80. Our arm ABC rotates with an angular velocity of 4 radians per second counterclockwise. Knowing that the angular velocity of the intermediate gear B is 8 radians per second counterclockwise, determine the instantaneous centers of rotation of the gears A and C and the angular velocities of gears A and C. So we started out with our V sub A and our V sub C equations, which are pretty easy to get. So we get our V sub A equals 1.2 meters per second down, and our V sub C equals 1.2 meters per second up. We can tell those directions from the diagram. And then at gear B, we have V1 equals 0.2 times 8 equals 1.6 meters per second down. And V sub 2, same equation, we get 0.8 meters per second up. And then at gear A, we have our angular velocity equals velocity 1 minus velocity A over 0.1 equals 4 radians per second clockwise. And then similarly at gear C, we have our angular velocity of C is V sub C minus V sub 2 over 0.2, which is going to be 2 radians per second counterclockwise. And then we have our L sub A equals V sub A over omega sub A, and that gives us 300 millimeters. Solve similarly for C, and that gives us 600 millimeters. Okay, next up we've got problem 15.70. Both 6-inch radius wheels roll without slipping on a horizontal surface. Knowing the distance AD is 5 inches and the distance BE is 4 inches, and D has a velocity of 6 inches per second to the right, determine the velocity of point E. Okay, so we go ahead and we start out with V naught equals 6 inches per second to the right, and then we can find our angular velocity of D is 1 radian per second clockwise. And then at point A, we've got V sub A equals R sub AP omega D, and we get that equals 11 meters per second. And then at E, at disk E, we've got R sub B over Q equals negative 4 inches I plus 6 inches J. And then we move on to our velocity of B equation, which we've got there. And then we know that that's negative 6 omega sub EI minus 4 omega sub EJ. And then connecting rod AB, we've got R sub B over A, which we can solve and get. So V of B over A, which we have square root of 171I minus 5J. And then moving on, we've got our V sub B equation, which we've got V sub A plus V of sub B over A. Corresponds to that vector there. And then we split that up into terms of I and J so that we can solve each one. And we get the I is 5 omega sub AB plus 6 omega E equals negative 11. And then we've got our J equations, which is the square root of 171 omega sub AB plus 4 omega sub E equals 0. And then we simultaneously solve those equations, and we get omega sub AB equals 0.75 radians per second, and omega sub E equals negative 2.4 radians per second. So we can take those values and plug them into our V sub E equation, and that's going to give us our V sub E equals 14.76 inches per second, and that's to the right. Alright, problem 15.56. Knowing that at the instant the angular velocity of rod DE is 2.4 radians per second clockwise, determine the velocity A and the velocity of point B. Alright, so we start out with our angular velocity of 2.4 radians clockwise, and then we find our V sub D equation equals V sub D equals omega sub dB times R sub dB, which is 288 millimeters per second, which is upwards. And then at rod ADB, we have our equation for R sub A over D equals 80 millimeters I plus 150 millimeters J. And then our V sub A equation equals V sub D plus V sub D over A equals V sub D plus omega AD K crossed with R AD. And then we go ahead and solve that for V sub A. We get 288J plus 80 omega ADJ minus 150 omega ADI. And then we equate the components, so we've got our I and our J, so we have an equation for each. So we can solve for our omega sub AD, and we solve for our V sub A. And then by our proportions, we can then use our R sub B over D equation and our V sub B equation to solve for V sub B, and that gives us V sub B equals 457 millimeters per second, 61.8 degrees up and to the left. Alright, problem 15.44. The disk shown moves in the xy plane, knowing that V sub A sub y equals negative 7 meters per second and V sub B sub x equals negative 7.4 meters per second, and V sub C sub x equals negative 1.4 meters per second. Determine the angular velocity of the disk and the velocity of point B. Okay, so we started out with our V sub B over A equation, and we can solve that and get negative 0.6 omega I plus 6 omega J, and our V sub C over A equation, which we get 1.2 omega J. And then we've got our V sub B equals V sub A plus V sub B over A. And then we can split those into our I and J components, and also find our V sub C equals V sub A plus V sub C over A. Same deal, split that into your I and J components. And then we can solve those simultaneously, find omega equals 10 radians per second counterclockwise, and solve for V sub B sub y and V sub B sub x, and get that our V sub B equals negative 7.4 I minus 1 J meters per second. Alright, so problem 15.31. A load is to be raised by 20 feet by hoisting the system shown. Assuming gear A is initially at rest, accelerates uniformly at a speed of 120 rotations per minute in 5 seconds, and then maintains a constant speed of 120 RPMs. Determine the number of revolutions executed by gear A in raising the load and the time required to raise the load. So we started out, we know that our theta sub b equals h over r1, which is 16 radians. And then we have our equation for S equals R2 times theta B equals RA times theta A. And we have our R2 and our RA, so we get S equals 288 inches. And then the angle change of gear A, we've got theta sub A. We can solve for our theta sub A equation and get that equals 96 radians, which we have to divide by 2 pi, and that gives us the revolutions, which is 15.28. And then for part B, we know that our initial velocity is 0 and our final velocity is 120, or 4 pi radians per second. And then we have our equation alpha equals omega final minus omega initial over t, which is 2.5 radians per second squared. And then theta sub A equals 1/2 alpha times squared, which is 31.4 radians. And then we find our difference in our thetas, which is 64.5 radians. And then we have our other equation for our delta theta equals omega sub f times delta t, which we have delta t, we just divide by 4 pi, and we get 5.139 seconds, and we just add our 5 seconds to begin with, and that gives us our final answer of 10.14 seconds. Alright, problem 15.22. The two pulleys shown may be operated in the V-belt in any of 3 positions. The angular accelerations of shaft A is 6 radians per second squared. If the system is initially at rest, determine the time required for shaft B to reach the speed of 400 RPMs with the belt in each of the 3 positions. Alright, so we start out, we have a couple equations. So we have our angular velocity of A equals alpha sub A times t. Our belt speed V equals R sub A times omega A equals the same as R sub B times omega B. The angular speed of the shaft equation, which is omega B equals V over R sub B, or R sub A times alpha sub A times T over R sub B. And then we can solve that equation for T and get this equation over here on the left. And then we can solve our omega B equation, plug in some of those values. We get 400 RPMs, which is the same as 41.8 radians per second. And then we've got our T equation. We plug in the values that we've got, and that's going to give us 6.9813 dB over dA. And then we just plug in our different values for dB over dA at the left, middle, and right. Solve those for T, and in the first one on the left we get T equals 3.49 seconds. In the middle we get T equals 6.98 seconds, and on the right we get T equals 13.96 seconds.